we start next section, that is section 2. Section 2. Line integrals. Let me recall. Former section was called integrals along a curve, and that is very similar, but this is line integrals. So now we'll consider an integral with respect to one variable. So suppose once again we have a curve in R3. So definition. So maybe let me give a definition for Rn, and then we'll consider particular case R3 as well. So let gamma R of t be curve in Rn. F be a function which is defined on gamma. If for arbitrary epsilon greater than 0, there exists delta greater than 0, such that for arbitrary partition P of our interval E equals to B, partition A, such that diameter of P less than delta, and for arbitrary choice of intermediate points, let them be tau I in the interval ti minus 1 ti I from 1 up to the following inequality holds. Sum I from 1 up to m f of tau I delta x h let me write like that, xh of ti minus xh of ti minus 1 minus I h less than epsilon, where r of t is x1 of t so on x n of t, and h belongs to the set from 1 up to n. I is a real number. Then I is called line integral of f with respect to variable xh over gamma. Notation is I is integral over gamma f of x vector d xh. And this writing also is limit as delta of p tends to 0 of those integral sums. So what are integral sums now? We consider now, if we look at a curve, there is a curve. Once again, everything is as it was before. That is variable t. But now, what happens? So let it be r of a, r of b. Once again, we have a partition here, which gives a partition of our curve. But now, what we do for the integral along this curve, what we did, we considered a point that is, let's say, somewhere here, it's tau I, that is ti minus 1 ti. Here we have r of ti minus 1. Oops, I forget, I'm sorry. Yeah, I forget about r. Also here, sorry, r should be included. So that is r of tau I. Here we have r of ti. Yeah. So these are points on our curve. For the integral along a curve, integral sum was formed like, so one term, we should multiply the value of our function onto the length of this piece of curve. Now, what we do, we look at the system of coordinates, right, in our space, and if that is xh, h coordinate is here, then what we do? We look at the projection. Yeah, that is this interval. Look, this interval is precisely the difference x of ti minus x of ti minus 1. This, the length of projection. So now we are interested only in projections on one line, on one axis, axis xh, and we are interested only in the projection. Okay, so as a main theorem, let me give it immediately. Theorem 1. If f is continuous on a smooth curve gamma, then the line integral exists for any h in 1 so on up to n, and once again the integral can be computed just by substitution. So what we do, we substitute everything, and it gives integral from a to b f of, let's say, x1 of t so on x n of t times x prime xh prime of t dt. So what is written here? Precisely differential of the function xh. What is the differential of the function xh? Derivative times dt. And that is precisely what we have here. So once again, like for integral along a curve, we had ds here. And how to compute? Just to substitute. ds is integral of square root and so on, right? Integral of modulo of r prime. Similar situation is here. Just substitute, nothing else. So proof. Proof is also very similar. So consider, first of all, note that the integral in the right hand side exists. Okay, I'll write shortly r of t x prime h of t dt exists. Why? Because we suppose the curve is smooth. What means smooth? In particular, it means the derivatives are continuous. So that is continuous function. That is also continuous function, because f is continuous and r is continuous. Composition of two continuous functions is again continuous. So we have a continuous function on an interval, hence it's Riemann integrable. So the integral is well defined. And it is equal, to the limit of the integral sums. So let me write those integral sums. Limit for arbitrary epsilon, there exists delta greater than 0 such that for all partitions p a equals to t naught less t1 so on less tm equals to b with diameter less than delta, and for arbitrary choice of points tau I in the interval ti minus 1 ti I from 1 up to m, we have that difference between our integral, Riemann integral, f of r of t x prime h of t dt minus, so what is the integral sum here? We should substitute the point to I, so I'll write shorter rho of to I, and x prime h of to I times delta ti. Yeah, that is less than epsilon. So what I wrote is precisely integral representation of Riemann integral as a limit of integral sums. Okay, now we'll prove our theorem because of the definition of the line integral if we can estimate difference between those integral sums. So let me write r of to I times xh ti minus xh ti minus 1 minus this integral sum which appears in that line. So we need to estimate this difference. Why? Because look, if we estimate it somehow like less than epsilon, then what we have? We have difference between this integral sum and that integral is small. And that is precisely what we ask from, IH here. IH everywhere. I forget IH. So, but this can be done very easily. Why? Because once again we apply mean value theorem, but now Lagrange mean value theorem. For integral along a curve, we used mean value integral theorem, mean value theorem for integrals. Now we apply mean value theorem for a function. So according to mean value theorem, that is Lagrange mean value theorem, we can represent this difference as f of r of to I times x h prime at an intermediate point between ti minus 1 and ti times the difference delta ti minus some and then I can, so you see what is difference. What is difference now? Look, here we have psi and there we have tau. There is only one difference between those two expressions. And we can estimate it like, so put it into one sum, common multipliers that and delta ti, and what remains after that we put modulus inside, so triangle inequality, and gives f of r of to I times modulo of difference xh prime of psi I minus xh prime of to I times delta Ti. Delta Ti is non-negative. So finally, like in the proof of similar theorem for integrals along a curve, we apply Cantor uniform convergence theorem, uniform continuity theorem, uniform continuity theorem. So what we have? We have that for arbitrary epsilon greater than 0, there exists delta 1 greater than 0, such that for all points x prime, x double prime in A, B, such that distance between them is less than delta 1, we have an equality x h prime at x prime. Oops, x prime is not good. Okay, let it be x tilde, x tilde, x hat, x tilde and x hat, x tilde, x tilde minus x h prime at x hat less than what? Less than epsilon over m times b minus a, where modulo f of x vector is less or equal m for all x in gamma. So f is continuous on a compact set, hence it is bounded, and we apply Cantor uniform continuity theorem. And now look, if we take arbitrary partition, so now for arbitrary partition P with diameter less than minimum of delta 1, this delta, and that delta 1, So if we consider arbitrary partition with this mesh, then what happens? Points psi I and tau I, both of them are between Ti minus 1 and Ti, somewhere between them. And mesh, what is mesh? Maximum of the length of the interval Ti minus 1 Ti, of those intervals. So maximal of lengths of those intervals less than this minimum. It means that the distance between psi I and tau I is for sure less than this delta 1. Hence, modulo, which appears here, this modulo of difference, is less than epsilon over, so that is less than epsilon over m times b minus a. This multiply is less than m, and lastly, we sum up delta Ti and we obtain b minus. So altogether, once again, we estimated by this everything less than epsilon. So sum of those two epsilons give us what we wanted to prove. So then a couple of corollaries, like for integrals along a curve. So corollary. Line integral does not depend on change of parametrization such that it is given by an increasing function. So increasing okay, let me insert here smooth function. Increasing smooth function with non-zero derivative. In fact, we don't need non-zero derivative, but okay, let it be. So, proof. So we consider a change of parameter like that. Let's say g of tau. Now I can use tau once again. So we know that is increasing smooth function, so g prime is positive because derivative is never zero, right? G prime is positive. Then what happens with the integral? Look, if we consider our integral, then as we know, integral over gamma, it is equal to the integral of f of how we wrote. Okay, let it be x1 of t, so on x n of t, x prime h of t dt. And now we change the variable t equals to g of tau. So let us change the variable. Then what we should write? G minus 1 of a, g minus 1 of b, f of x1 of g of tau, so on xn g of tau, yeah, times xh prime of g of tau times g prime of tau d tau. So I made change of variable in Riemann integral. Then what is written here? according to chain rule, we have derivative of, so I'll write shorter like that is xh prime of tau. So if I denote xh of g of tau shorter by xh of tau, that is not correct, rigorously speaking. I should change the letter here, of course, right? So, okay, let me change it like tilde here. Maybe it will be better. Tilde. It will be better otherwise. Yeah. So then what we obtain? F of x1 tilde of tau, so on, x n tilde of tau, x h tilde prime of tau, d tau. And look, now before we had our curve given by equation x of t, where t varies between a and b. Now we substitute t equals to g of tau, and we have same curve, in fact, where now we have x tilde, and parameter is tau, which varies from g minus 1 of a up to g minus 1 of b. So we change parameter. Instead of t, we substitute g of tau, and we obtain, like here, right? We obtain same curve. So we substitute parameters. So it means, roughly speaking, we change the law how we go along that curve, depending on time. So if we look at t as a time, and our curve is trajectory, then what happens if you change variable t? It means that you change the law how we go along this curve in time. But the set of points in the space is absolutely the same. So trajectory is the same. The law how you travel along this trajectory is different. That is meaning of change of variable. And you see, here it's important that we look, we preserve. So because of increasing function, we don't need to change the order, right? So we have correct order of limits of integration. And if we omit this supposition about increasing, then it will be different story. And let me give a definition. Change of parameter okay, let it be t equals to b minus tau. Let it be like that. Yeah. maybe plus a. No. No, maybe a minus tau. So if t equals to b, then tau equals to 0. Okay, let it be like that. Change of parameter. Yeah. Gives change of orientation of the curve gamma r of t a from t to b. So after that, look, if t varies, so t varies from a to b, then how tau varies? If we substitute t equals to a, then tau is b minus a, right? No. T equals to a, no, yeah, b minus a, yeah. And if we substitute b, then tau is 0. Yeah, it's better to write like that. So tau up to like that, b minus a. Yeah, but let me change, otherwise it's not clear. Let me write like that. Yeah, that is better. So if we look at the picture, look what happens. Firstly, we had the integral from r of a, not integral, curve, up to r of b. Time varies from a to b, right? And we go from that point to r of b. Now what happens? Now tau varies in converse direction, right? So here, this is greatest, b minus a, tau is greatest, has greatest value, right? At that point, tau equals to b minus a. This is positive and greatest possible value. And at that point, tau has minimal value, right? So if we go in the direction of increasing of tau, then the direction will be opposite. That is change of orientation. So firstly, curve was oriented like that, right? And after this change of parameter, it will be in opposite direction. That means change of orientation. So you need to take into account the orientation of the curve, namely how you travel along that curve, in which direction. That is essential difference with integrals along curves. For integrals along curves, it was not important, the direction of traveling. For line integrals, it's important. For an admissible change of parameter which changes also the orientation, of a curve. The line integral changes sign. So you see, first corollary says line integral does not depend on a change of parameterization, but if it is given by an increasing smooth function. And we know that admissible parameterizations are given just by strictly monotone smooth functions. So what it means? If it is increasing, line integral doesn't change. But if it is decreasing, then we change orientation of the curve. Hence, we change the sign of a line integral. Why? Because look, everything is the same, right? In the proof of corollary. Nothing changes. But then look at the final. If g is decreasing, then we have upper limit smaller than lower limit. So we need to change the order to make it normal order, right? Hence, we obtain minus sign. That gives this corollary. And now consider the particular case n equals to 3, right? Then we have how many variables? We have 3 variables, right? So we may consider 3 different integrals with respect to each of variables. And usually they are considered together. Why? Let me explain. So we consider integrals like that. Line integral like that. So we have 3 functions simultaneously, p, q, r. We have 3 functions simultaneously. And we consider simultaneously 3 integrals. And instead of writing 3 integrals separately, we write them together in one integral. So that is just one integral, but usually brackets are omitted. So they are supposed, of course. And what is the meaning? Standard notation. So if we denote this vector like f, that is a vector field. Vector field. So what is vector field? In fact, that is a vector function, nothing else. Just other words. Vector field. Then that is written like f dr. Scalar product. Like scalar product. F times dr. Of course, it makes no sense, right? What is to multiply by dr? But just formula. If you know 3 coordinates, right? What are coordinates of differential of a vector function? Dx, dy, dz. So we multiply. Scalar multiplication, sum of products of corresponding coordinates, right? That is just a notation. And what is meaning of this integral? Let us try to understand what is it. So if you move along a line, right? You move along a line and you apply a force F at every point, right? Then what is about work of this force? Work of the force we should multiply f times the length, right? If force is constant. But now look, we are in the space, right? So the force is a vector which has 3 coordinates in general, right? These are 3 coordinates of the vector of force. That is why F is used here. Then, if you look at integral sum for the line integral, then you will recognize work along an coordinate axis, roughly speaking. And if you want to compute the total work, you need to compute to add together works along each of coordinate axes. So the physical meaning of line integrals, that is work of the field of force F along the curve gamma. That is physical meaning of the line integral. That is why usually all those 3 integrals should be considered together, because makes no sense to consider just one coordinate of one object. Okay, that's it. So then we start next section, section 3. In fact, it will be the first section of a series which is devoted to measure. And it will be called elementary sets. Elementary sets. So I want to explain why I plan to give you a little bit of measure theory. First of all, it is necessary for probability theorem and other branches of stochastic calculus, I would say. There is a nice theorem which has many applications in physics and economics and so on. And secondly, I don't think it's a good idea to spend the time to consider sets of 0 Lebesgue measure without any knowledge about Lebesgue measure. It's a little bit strange for me. It seems to me a little bit strange, although yeah, you see, for example, Zorich textbook, which is very nice textbook, but he doesn't consider Lebesgue measure in general at all. Only 0 measure, nothing else. That is, yeah, it's sufficient to introduce multiple integrals, but Lebesgue integrals are essentially better. Of course, I have no possibility to give you complete theory of Lebesgue integrals, but I plan to give at least a part of it as multiple integrals. So as multiple integrals, we'll consider Lebesgue integrals, not Riemann integrals. But Riemann integrals I'll mention as a particular case. So what are elementary sets? I'll start with definition of interval. Definition. An interval in Rn is a product like that. Product I from 1 up to n, ai, bi, where in angle brackets ai, bi is an interval of the form ai, bi, ai, bi, ai, bi like that, or like that. So each of those form is acceptable. Yeah, I should also to mention that ai, bi are real numbers. Real numbers. So for R2, that is a rectangle. Rectangle with sides parallel to coordinate axis. For R3, that is a parallelogram. Again, with sides parallel to coordinate planes. Coordinate planes. With faces, sorry. With faces parallel to coordinate planes. And so on. Then, next definition is volume. Volume of an interval ai, bi is equal to product of lengths of sides bi minus ai. Yeah, ai, bi should be, of course, like that. Yeah. ai, bi should be like that. So we'll consider non-degenerate intervals. Yeah. And it is, yeah, so let me interval, let's say capital P or capital Q, maybe it's better. Capital Q is equal to, and it is denoted by that. Yeah. So volume. So what is volume? For n equals to 2, that is usual area. For n equals to 3, usual volume. For large n, okay, you didn't consider it yet, right? Next definition. An elementary set M is a finite union of disjoint intervals. But look, disjoint intervals, what it means. For example, in R2, what are elementary sets? They can be like that. Yeah. They can be like that. That is an elementary set, right? Why? Because you can form, okay, let it be different, like that, intervals, Okay. Yeah. And yeah, for example, we can also form like that. Doesn't matter. And you remember that we can include one end and do not include, right? It depends on us. So what we can do? For example, we can include that side of our rectangle, but exclude, let's say, here, exclude that side. So it depends. That is why, you see, here rectangles touch each other, but when they touch, the side is included only into one of rectangles. That is how we can represent figures like that as unions of disjoint intervals. Is it clear? Yeah. I don't want to spend the time to write down everything rigorously, because here, you see, for example, let me write a lemma. One, union, intersection, difference, and symmetric difference of two elementary sets are elementary sets. So, okay, with union it is more or less obvious, right? Although, again, you need to spend the time for a rigorous proof. For intersection also. In fact, for intersection it's even easier. Difference. What is difference? Difference means intersection with complement. So what is complement? Complement is Rn without B. So everything outside. But what is symmetric difference? Symmetric difference, by definition, that is symmetric difference, A minus B together with B minus A. So it corresponds to, how it is called in logic, exclusive OR. So OR, exclusive XOR, 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 XOR. So I don't want to spend the time to prove this lemma because it's quite elementary, and although I need to do something to represent. Also, next is then next definition volume of an elementary set is equal to the sum of volumes of disjoint intervals which form of an elementary set, let's say M, which form M. So if m equals to, oh, by the way, I'll use also this sign. That is very convenient. Let's say pi. So what is it? That is union. But when I write like that, these are disjoint sets. So they do not intersect each other, right? That is union of disjoint. Then m is equal to the sum. So once again, I need to prove that this definition is correct. What I mean by correctness? Look at this example. So I draw one partition of our elementary set into disjoint intervals, right? But we can do it in a different way, right? Like that. Yeah, so let's say like that, right? That is a different way. And of course, I should be sure that the sum of volumes is the same. It's clear that's the same, right? I mean, geometrically, how it can be different. But nevertheless, you need to prove. And rigorous proof, you need to consider all mutual intersections of all those intervals. If you have two distributions, then you need to consider all intersections of those two distributions. That's a way to prove it rigorously. So also I want to give a theorem, one, main properties of volume for elementary sets. So once again, yeah, in fact, okay, let it be first property. Volume is correctly defined. That is what I said about just now. So secondly, for arbitrary m n elementary sets, for arbitrary two elementary sets, volume of the union is equal to sum of volumes minus volume of the intersection. And also, yeah, for disjoint or not disjoint? Not disjoint. If elementary set, an elementary set M is covered by finitely many elementary sets let's say mj's, then let me write here M is a subset of the union of mj's, then the volume less or equal the sum of volumes. Okay, I don't want to spend time for those sets because they are obvious. Remember, yeah, in fact, imagine the picture for R2, right? We have a figure which consists of finitely many rectangles with sides parallel to coordinate axes. So if you have several such elementary sets, then of course those properties are satisfied. Okay. But next property is essentially more complicated, and I want to give it with proof, because here analysis works, not geometrical, not elementary geometry. So I'll call it Theorem 2, sigma additivity of volume over elementary set. So if an elementary set M is represented as a disjoint union of countably many, of at most, okay, maybe of countably many elementary sets M is disjoint union Mj, then volume of M equals to the sum of volumes. And you see a series appears. So proof. For the proof, if we represent each of Mj's as a disjoint union of intervals, then we need to prove the following. If M is disjoint union of, okay, let it be Tj's, let it be Qj's, where Qj are intervals, then m equals to the sum of qj's. Practically, you don't need to prove this sentence. Why? Because if you represent mj as a finite union, right, then altogether, look what you have. You have union, then here you have union I from 1 up to, let's say, nj, and here you have qij's. Each of elementary sets you represent as a union of intervals. Altogether, you have countably many intervals altogether, right? And that is written here. Countably many intervals. So, then what we do? Oops. Now I need to give extra definition. Those definitions are given only for this proof. I don't plan to use them in future after that proof. So that is why I give them inside the proof. So definition 1. Epsilon enlargement of an interval, let's say up to n, okay, let it be p equals to product ai bi is the following. P, I'll denote it p epsilon is equal to product I from 1 up to n. Okay, open interval ai plus bi over 2 minus nth root of 1 plus epsilon times bi minus ai over 2, and say it looks rather complicated, I mean this expression, but if you will think a little bit, then you understand it's simple. Okay, and also definition 2, epsilon contraction of an interval p, which is product ai bi is, okay, let it be p minus epsilon contraction. That is product I from 1 up to n. Now closed interval ai plus bi over 2 minus nth root of 1 minus epsilon bi minus ai over 2 ai plus bi over 2 plus nth root of 1 minus epsilon bi minus ai over 2. Oops. Closed interval. So geometrically what it means, let me write it here. Let me give a picture for R2. So you see, we have an interval. Doesn't matter, maybe some of boundaries are included, some of them are not included. So for R2, right? Then what we do? For epsilon enlargement, I should consider slightly larger rectangle, like that. That is p epsilon. and it is open. Epsilon contraction is inside, like that. So you see, center is the same as for the original rectangle. AI plus BI over 2. Center of arbitrary side is the same, right? But the length is not BI minus AI. Look, what is the length? The length of this interval you should multiply from that this one. You obtain nth root times BI minus AI. Right? So it means that for epsilon enlargement, the length will be slightly larger, right? For epsilon contraction, the length will be slightly smaller. But why I choose nth root? Because, look, what is the main property which I'll use? P epsilon volume. Look, every side is nth root of 1 plus epsilon times greater, right? Every side. So to compute the volume, we need to multiply them. So altogether, we obtain multiply 1 plus epsilon, right? That is the main property. And also, for epsilon contraction, we have this. So look, you see, epsilon enlargement is an open interval rectangle or parallelogram, right? Which is larger than our original rectangle. It contains our original rectangle inside, right? And you see what is the volume. 1 plus epsilon times the volume of the original rectangle. Interval in Rn. And for epsilon contraction, analogous property, but now you see, contraction is closed set. You see, contraction contains all boundaries, right? So enlargement does not contain boundary. It's an open set, but contraction contains full boundary. That's important. Oops, not later. Next time you will see why. Yeah. Okay, so next time I'll not recall the definitions. The only thing I'll need this picture and that property. That's all.